Determine whether the following series converges or diverges. The sum from 1 to infinity, 4n over 9n plus 1, the entire quantity, to the n over 2. And so we have to decide on what happens with this, maybe as n gets big, but to do that it's going to take a while. The inside is going towards 4/9, and that 4/9 would be raised to the infinity power. If you have something less than 1 and it's raised to larger and larger powers, it's going to go to 0. So it turns out that test for divergence doesn't help us because we get a 0 limit. There's the fact that this is raised to the n over 2 power is a hint that we should try to root test. Now, the root test works even if it isn't just an n. When there's some kind of formula on n, perfectly fine. N over 2, 2 times n, n plus 1, whatever it takes, you can do the root test and try it out. Now, what the root test does is it immediately takes whatever is your a sub n, makes it positive by taking the absolute value, and looks at the nth root of it. So it's like raising it to the 1 over n power. It's already positive, so we can drop the absolute value bars. What happens when you take something that's to the n over 2 power and raise it to the 1 over n power? With these exponents, the n's cancel. So you're left with something to the 1/2 power. It's 1 over 2 times 1 over 1, the 1/2 power. And that's just the square root. And so we're looking at the square root of 4n over 9n plus 1. The square root function is a nice continuous function for all positive n. We can bring this limit on the inside. And notice that we have a polynomial divided by another polynomial where the degree of the numerator equals the degree of the denominator. So it just goes to the ratio of their coefficients, which would be 4/9. But that 4/9 is underneath a root. So the square root of 4/9 is 2/3. So we're doing the root test. The limit that we get out, depending on its size, will tell us convergence or divergence. When we get something out that is less than 1, the root test, much like the ratio test, will tell us that our series converges.